and looking at the idea of what a bond is in chemistry. So a bond can be simply defined as being an electrostatic attraction. So electrostatic attraction. This attraction is very strong. This is what holds one atom clinging to another atom within a compound or the same substance. The reason that atoms will form bonds is in order to form a more stable electron configuration. So a common term here to describe a stable electron configuration is that an atom tends to want a full octet. And what does that mean? A full octet, well, oct refers to the number 8. So a full octet is when an atom, whether naturally or through bonding, ends up with a total of 8 valence electrons. So the big key here is that elements that are in groups 1 through 17, each one will go through some sort of bonding process to end up with an electron configuration. So I'm going to put electron config like a group 18 element. They all want an electron configuration that looks like one of the group 18 noble gases. Now, a chemical bond. So a chemical bond that exists, it really represents the potential, or we could say stored, chemical energy. So a bond between two atoms or two ions, that bond represents the amount of stored chemical energy. Now, in the process of a reaction, bonds are broken and bonds are formed, and different things happen with energy. So energy needs to be released when bonds formed, and energy has to be absorbed when bonds break. So if you have a structure where a hydrogen atom is bonded to another hydrogen atom, to make these two hydrogens split apart from each other, that means it takes energy or a force. So energy goes in, and if enough energy goes in, the hydrogens split apart. So they split from each other. So just think about if you want to break your pencil in half, you have to grip it and you have to apply force or put energy into it to make it split apart. Okay? So energy is always absorbed when bonds break. Now here is a crazy idea or this is an idea that we need to get memorized. Only valence electrons are used to form the different types of bonds. Okay, so let's take a look. There's always going to be a question about energy transfer during the breaking and forming. So we have this little thing that's called BARF, and BARF will help you remember what's going on with energy. So we have BA and BARF versus RF. So here we go. So in BARF, BA, so in order to break, we have to absorb. Versus RF, we have to release that energy in order to form. So break and absorb always to go together, and release and form always go together. So here we go. Which statement best describes the energy change as bonds are formed and broken in this reaction? Well, take a look. On the right-hand side, this is a product, and on the left-hand side, these are reactants. So the products, these are the things that are being formed, right? So we see HCl. HCl is a product, it's forming. HCl is a product, it's being forming, okay? Reactants, if it's on the reactant side, that is where bonds need to break. So H2 is on the reactant side, breaking. Cl is on the reactant side, so bonds are breaking. So right here, we know that these terms, forming and breaking, are applied correctly to each substance. Now I'm going to go more general with BARF. So if it says forming, right, it has to say relief because R and F always go together. So here it says forming, but then it says absorb. So I'm going to get rid of that because it's not matched up. Same thing where I have the word breaking. Breaking is always associated with absorbing energy. And here this one says release. So breaking, and once again, if it's breaking, it has to be absorbed. So when I just look at the terms breaking and forming and what's being said about the energy, there is only one statement that matches up. So statement A. Now, a little bit of recap on Lewis dot structures. So the Lewis dot diagrams, the dots, remember, those represent the valence electrons. And we place those around the elemental symbol, and that symbol represents the kernel. So here we go. Valence electrons. There is an order that we put them around. First valence electron, second valence electron, third valence electron, fourth, fifth, and then we go back if we have our sixth valence electron, if there's a seventh one, and if there is an 8. So take a look. In the dot diagram, there's a total of 8 dots we can put around it and a max of 2 per side. Okay? So sodium, symbol is Na. When you look up its electron configuration on your reference table, it's 2-8-1. The valence electrons count is always the last number. So that's the number of valence electrons. So the symbol Na would get only 1 dot placed at the 12 o'clock position. Oxygen, its symbol is O. On the periodic table, it gives us the electron configuration of 2-6. And so since 6 is the last number in its configuration, that's the number of dots we put around. So electron 1, electron 2, electron 3, electron 4, electron 5, and now I go back and pair up. So there is electron 6. Last example, chlorine. Its symbol is Cl, and when you look at its electron configuration on the periodic table, 2-8-7, and since 7 is the last digit in its configuration, that's the number of dots. So start at 12 o'clock, 1, 2, 3, 4, 5, 6, 7. So this would be the dot diagram for chlorine.